So the first workshop will be about unsupervised learning algorithms. So through this workshop, you'll be able to distinguish between unsupervised and supervised learning. So it's about clustering, and it's very important for unsupervised machine learning algorithms. So you'll each have the opportunity in 30 minutes to explore a step-by-step practical application of K-means clustering. So Mohammed is the pro in that, and he'll tell you more about it. Maybe Tim, you can introduce Mohammed to tell us a bit about his background.
Yeah, sure. So we're lucky to have Mo on the team. And actually, Mo, I'm not sure how to pronounce your last name. Maybe if you would want to.
Kleit, it's fine. Okay, I don't even know, to be honest. So.
Okay, great. So we're really lucky to have Mo, or Mohammed Kleit. He's an AI specialist at AI Launch Lab, and he's an MSc student in machine learning at the University of Montreal, or Université de Montréal. Machine learning intern at the CDPQ. Is that Caisse Desjardins?
It's Caisse de dépôt et placement du Québec.
Okay, right. Okay, cool. And previously a software engineer at Tech Systems Global Services. So very fortunate to have him giving this workshop. So I guess take it away, Mo.
All right, thank you. Thank you, Tim. So good afternoon, everyone. So I'm gonna start by sharing my screen. And basically this workshop, for this workshop, we're gonna go through a Colab notebook. I thought it would be the best way to show the theory and go through some practical examples at the same time. So as Monica mentioned, it's going to be an introduction to unsupervised learning, and we're going to put a focus on clustering. So first of all, what I would like to do actually is simply share this document with you, and I'm going to post it in the chat, and you should be able to open it, and then I'm going to show you what you can do with this. Let me just post it in the chat. 1 second. So simply when you open it, you can just go in File and then save a copy in Drive. So it's going to save a copy of this notebook in your own Drive. And then you can decide to follow on this notebook at the same time, or you can keep it for after and then play with it after. So it's up to you. All right, so unsupervised learning. So before diving into the unsupervised learning part, I wanted to do a quick refresher of supervised learning. To see what's the difference between the two. So in the context of supervised learning, we have a set of inputs or observations that we call. So here we have defined them as a set of vectors, right? x0, x1 till xm. And each vector contains a certain number of elements, up to n elements. And for each of those observations, this is the specificity of supervised learning, we have a corresponding target or label. And you can see it in this table here. Basically, every row corresponds to an observation. The first row corresponds to this vector, x0, right here.
Mohammed, can you zoom in a little bit? Some people say it's a bit hard on the eyes. Thank you.
Sure. Let me... I
think if you do Control+, perfect.
Is it better like this? Yeah?
Yeah.
Okay.
Yeah, thank you.
Awesome, thanks. So as I was basically saying, every observation has a target, right? And every row corresponds to one observation. And this is the specificity of supervised learning. The goal is basically to train a model or to train a function of this form. So we want to be able to predict the target based on the observation that we give it. And in order to do this, while we train the model, we have a set of parameters theta. And as you can see, there are as many parameters as there are features. A feature is basically one characteristic that every observation, every row shares. And so we want to fine tune these parameters in order to train our model and improve its capacity to predict correctly the targets or labels. So in order to do this, as you've probably seen in previous workshops, we have a loss function. And this is where the target comes in, right? So this y hat is basically the prediction made by our model. And the y is the ground truth. And basically, we're going to see how our model's prediction compare to the ground truth. And based on this, we're going to tune the parameters. And so in the context of supervised learning, there are two main tags, classification and regression. Here, it's a simple example of classification where we need to predict a class label. As you can see, we have two kinds of observations, the blue dots that belong to class 2 and the X's that belong to class 1. And we know for each observation what is the label. And then we train a model to be able to classify them, separate them into groups. Now, the difference with unsupervised learning or unsupervised learning, sorry, is that we don't have, in that case, any target or label. As you can see, this is the same set of observations, but in that case, we don't have a target. Whereas here, we have a target for each observation. And in that case, we don't have any ground truth, so we cannot train a model the same way we did for supervised learning and learn from the prediction that we make by comparing it to the ground truth. What we want to do in the case of unsupervised learning is infer the inherent properties of the data of the observations, right? And there are ways to do this, and today we're going to explore clustering. So clustering is basically, the goal of clustering is to be able to partition the data that we have. As you can see here in this picture, we have a set of observations, but we don't have any labels for each. We don't know if they belong to a specific class or not. And the goal is to be able to discover this. And so we're going to partition this data into groups that we call clusters, such that the pairwise dissimilarities between the observation in each cluster is much smaller than the dissimilarities of the observation of different clusters. To make that more concrete, we start from here. And what you can see is that after clustering, we're gonna partition the data in 4 different groups. And what we mean by pairwise dissimilarities is that each pair of observation in each cluster, the difference is much smaller than the difference there would be between this observation, let's say, and this one. And this is what makes observation part of a certain group. So this is the idea of clustering. And there are different models, different methods we can approach for clustering. Today, we're gonna explore one of the most popular one, which is basically k-means. So in the case of k-means, basically our observations are all numerical. They're of a quantitative type. And so we have unlabeled observations, as we said, because this is an unsupervised learning task. There's no target. And we have a parameter k that corresponds to the number of clusters we want our model to find. Now, what is important to understand here for k-means is that we need to predefine this number before starting the training of the algorithm. And we'll come back to this a bit later on how to do this. But the intuition behind k-mean is fairly simple. We assume that each cluster has a certain center, and that center is basically the arithmetic mean of all the observations that belong to that cluster. So if I take this example, you see this part, which is a bit shaded, well, it corresponds to the mean of all the observations belonging to that group. And each point that belongs to a certain group is closer to the center of that cluster than it can be from the other clusters. So how do we do this in practice? How do we implement it? So how it works, we're going to start with a random initialization of k centers. So we said we need to predefine the number of clusters we want. And we're going to initialize randomly k different cluster centers. And then we're going to do the 2 following steps until the algorithm has converged. That means until there's no more improvement in the results that we have. So after initialization of the cluster centers, we're going to assign each point to the center that is closest. Once this is done for all the points, we're going to update the cluster centers with the mean of all the observations that are closest to it. And we're going to do that in an iterative way until there's no more improvement. So I have added here a link that I can show you that help us visualize how k-means work in practice. So remember the 2 steps we mentioned that we're going to repeat until the algorithm converge. First, we have initialized the clusters randomly, right? They were put there randomly. And then we need to find the closest centroid to each of the points. The black dots are all our observations that are unlabeled. So this is the first thing we're going to do. And we can see here that every point has been assigned to a certain cluster center. Now we're going to update the position of the centroids, the cluster centers. And we see them moving. And basically we're going to repeat this until we have reached a convergence. So you see at some point, whatever I do, the centers do not move anymore. That means that we have reached convergence and we have been able to separate our observations in 3 different groups. And the number of clusters was predefined, basically. And you can play with it. The link is in the Google Colab, and you can initialize new centroids every time and just do it again. All right, so let's go through a simple example. So you will have access to this. You will be able to go through the code in detail, take your time. Here is simply quickly, those are imports. I'm importing all the libraries I need to be able to do the training, and the plots methods that I wrote to be able to plot the graphs. So we're going to show how k-means work and how we can train it, basically, and we're going to use a specific library called scikit in that case. So first of all, we're going to generate a data randomly. So what basically this line is doing, make blobs, is going to create 400 observations unlabeled. And what we want is we're going to predefine 5 centers. We want to have 5 groups. That means there's going to be an equal amount of observations for each group. And we want 2 features. Remember, the features are the characteristics of our observations, right?
Sorry, Mo. Sorry to interrupt. Would you be able to zoom in again? Just because I think even on my screen, it's still a bit small.
Okay. Is it good like this or even more? Would be better.
Just in the chat, just let us know if it's still small. That's definitely better for sure. But as much as you can, because I think for those with 13-inch screens or smaller, it's still tough. Yeah, great, appreciate it.
Sorry, and also could you speak a bit slowly so the interpreter?
Oh yes, sorry about this. I'll try to go slower.
Great.
All right, thank you. So as I was saying, what we're going to do right here is we're going to create our data set randomly that we're going to use after to see if k-means is able to find clusters and partition the data. What you need to understand from this line is basically that we are creating 400 different observations. Each observation is a point, basically. And we're creating it for 5 different clusters. This parameter centers created for 5 different clusters. Now, it's important to know this is not k-means yet. This is just generating a data set, and we do it for 5 clusters because we want to be able to compare afterwards how k-means perform. So it might not look intuitive enough because it seems like there's only 3 different clusters, but there's actually 5, and we'll see it after. So if we look at this plot, basically, as I was saying, we can guess 3 main clusters when actually there are 5. So it does not seem that complicated. However, it's important to notice that right here, we only have 2 features. That means every observation that we have only has 2 elements. An element along the feature 0 axis and an element along the feature 1 axis. So this makes it easy to visualize it. And since this is for demonstration purposes, we're going to go with something simple. But in practice, our data usually has many, many more dimensions and many, many more features. So it makes it difficult to visualize it. There are some techniques, dimensionality reduction techniques, that we can use to apply in order to see to be able to visualize the data. One of which is principal component analysis. We won't talk about it today, but I would highly recommend looking into this. So in the case where we have many different features and dimensions, k-means is very useful because it is able to partition the data, even if there are a lot of features. So what we're going to do here, basically this method that I have written here is the method that is going to train the k-means algorithm. So this method is being called here, and inside basically it's calling the k-means class from the scikit library, and we're going to pass it the number of clusters we want. The initialization method we want, in that case, it's random. This is just a default value in case we don't pass this. And parameter initialization that is by default 10. We'll come back to this after. Then we're going to fit our model, and then we're going to make the predictions. For every observation, we're going to make a prediction in the sense that we're going to say, okay, it belongs to this group among the 5 that we have. So if we plot it, we see here, those are the clusters that were inferred by k-means. So after training, at some point, it reached convergence, and it was able to find 5 different clusters. And if we compare it to the actual clusters that we created, we see that k-means is doing a fairly decent job, right? It's partitioning the data the way it was, almost the way it was generated. Now, there are some caveats to k-means, actually, some things that are important to notice. So here, we're going to train again k-means with the same number of clusters, the same initialization method. However, this parameter has been changed to 1. And I'll go back to this after, but once we train and we plot the clusters, we can see that k-means did not reach a global optimum. The algorithm has converged because it couldn't move anymore, it couldn't improve more than this. But we can see that here, for example, it partitioned in 3 different groups, whereas there's only 2. And here it only found 1 group when there are 2 groups here. And the reason for that is the way we initialize the centers before starting the algorithm. So remember, we said we need to initialize a k number of centers, cluster centers, before running the algorithm. In that case, this is the parameter that deals with this. This means that only initialize it once. And we can see that this is a problem. So the solution to this, and something that is done by default in scikit, is that we're going to run this model multiple times for different initialization methods. And we're going to keep the best out of it. So the reason for which we found something almost identical is that here, the default value was 10. That means we ran k-means for 10 different initialization centers. And we chose the best one, and this is the best result that we got. Now, there's another concern, I would say, with k-means, is that we need to know in advance the number of clusters that we want. This is something that we mentioned at the beginning. And the thing is, k is a hyperparameter in this case. That means basically it's a parameter that we give to our algorithm, and the algorithm is not going to learn this parameter on its own. Remember, when we're talking about supervised learning, the algorithm was learning parameters and was fine-tuning those parameters based on the loss that we had and the predictions and how far off we were from the ground truth. In this case, it's a hyperparameter. It's something that we give it and that we need to change on our own. Now, the thing is, let's say we don't know how many clusters they are, and sometimes it's going to happen. Right? Well, the problem with that is, depending on the number of clusters we use, we can be really far off from the actual distribution of the data that was generated. So here, for example, we created, we passed the two clusters. We say we want k to be equal to 2. We want to partition the data in 2 groups. Once we do this, it creates 2 groups, one in yellow, one in purple. But we can see that we're really far from the actual distribution of the data. So how to approach this issue? This is a difficult question. The thing is, often, even though we don't know the number of clusters, we need to define this number based on the goal that we have and the problem that we have at hand. So it's going to be defined as part of the problem. So let's say we have a certain set of observations, and let's say we have observation about customers from a company, right? And we have a certain number of salespeople. Let's say we have 5 salespeople. Well, we want to be able to partition to segment the customer database that includes the observations about the customer, so that each segment is associated to one salesperson, for example. In that case, we're going to define K to be 5, and then K-means going to try to generate 5 clusters, and each cluster is going to include customers that are very, very similar to each other. Now, there are some other techniques which I won't really go into that can be used in order to find what would be the best number of clusters. There's something called silhouette analysis, and I added the link. It's you can read it. It can be helpful. There are other ways to do. Like one option would be to try different cluster values, different K values, and plot the pairwise dissimilarity or the cluster dissimilarity for each value of K. And we see, so for the value K that has on average the less dissimilarity is the one we could keep, for example. Finally, I added in the last section a small exercise, I would say. So we talked about clustering in the case of numerical variables, and the thing is we can apply this to images as well. And this is an example that I would like to try on your own when you have a bit of time. It's you can use what we've done previously in this notebook, and that's going to help you a lot for this. But one thing I'd like to mention is that in that case, this is a more realistic example. For example, we're going to load the digits, and then once you play with it, I want you to print the shape of the observation. So how many observations that we have and how many features that we have. And you will see that we have much more features than 2, right? So it's difficult to visualize this on a plot. However, we can train K-means the same way we've done it previously to see if we can manage to regroup all the observations that are similar to each other. And here we have digits from 0 to 9, and intuitively, K-means should be able to regroup all the observations that correspond to 0 and all the observations that correspond to 1, and so on. And so, yes, that is something I would like you to try on your own when you have a bit of time. You can use the 2 references I've put here that are there's a video that's very interesting that's gonna help you understand K-means, get the intuition better. And this is a book which I use as a reference, very well written. Yeah, that's pretty much it for the tutorial, the workshop on clustering. I don't know. I don't know how I'm doing regarding time. I don't know if we have time for questions.
Yeah, we can take a few questions more. Fiona, I can read them out to you, or you can see in the chat many people have asked.
Yeah.
Some.
Okay. I will. 1 second. Okay. All right, where should I start? So how to know how many clusters you have in a data? So yes, as I was saying, basically this is a difficult question. In some cases, it is part of a specific problem and a specific goal, and we know we're looking for 3 different groups. We're going to use K equals 3 in that case, and we're going to see what are the best, what are the groups, the partitioning that we get from K-means. In other cases, it might be a bit more difficult, but there are some techniques that can be used. I recommend looking at the silhouette analysis short description that can help. So I think you predetermine the number of clusters beforehand. Exactly. I think you have to compute K-means with a bunch of K and find the K that minimize the distance from each point to its centroid. I'm not sure that was a question, but yes, we can try different values of k, and then we see for which value of k we get the less dissimilarity between the clusters that we come up with. Will you give us a solution at some point for this assignment? Yeah, definitely, I can do that. I'll give you a few days though, maybe to try it on your own, and then I'll release the solution for this. And lastly, Simon, how do you choose the characteristics for each data? Could you please clarify your question in order to make sure I understand it well enough? I think you're referring to the features, right? Well, if you're referring to the features, so as I was saying, basically,
about the
X and Y.
visualization, maybe the
Yeah,
time that you
okay.
visualize it. How do you know?
How do you what? Sorry.
How do you know that what is axis X and Y when you want to visualize it for your data? I mean, how you can plot it? I think that's the question.
Okay. Well, so just to go back to this, so the characteristics, so the features are characteristics, so there's just dimensions of the data. Let's say we only have 2 dimensions, X, Y, or X, Z, it doesn't matter. So maybe to give you a bit more intuition, let's say we want to classify whether a mail is spam or not spam, or something like this. Well, a feature in general is going to be a characteristic for this. Is the email too long? Are there typos in the email? So the length of the email could be a feature, the number of typos could be another feature. So those are the features, and this is what we plot here, feature 0 and feature Y. Those are the coordinates of each observation. And how to plot it, if that is the question, it's basically, I'm using matplotlib, which is a library that is standard. Everyone uses this when it comes to plotting plotting graphs. But this is the method that I'm using for plotting this graph. And we basically plot a scatter plot. So we take all the X values. So this is feature 0. All the observations that have that belong to feature 0 and all the observations that belong to feature 1, and we plot them as X and Y values, and this is what you're going to see here. Do you use other library for unsupervised learning like PyTorch or Keras? You can definitely use Keras. I have never. Yes, you can definitely use PyTorch or Keras. When it comes to something like this, I usually go. I usually use Scikit because it's fairly well done and easy to implement. I haven't used that for with PyTorch or Keras, like k-means before, but I'm pretty sure it's possible. Yes. Can you explain once more about the n-init argument? Oh, okay. Yes, that's a good question. So I was saying basically about the n-init. This is a parameter that we pass to the k-means class, and this is to tell to k-means this is how many times I want you to run the algorithm to train, because every time we train k-means, we're going to start with a certain initialization. Maybe if I start here, it's going to be easier. But let's say we do new centroids. This is one initialization point. And then what we're going to do is we're going to run the algorithm until we have reached convergence, right? Then n-init says, let's say we pass 2 as the value for n-init, for n-initialization, that means it ran it once, and then it's going to reinitialize it once again. We're going to run it again. And then see, it stopped converging. Now we have ran k-means twice. The first time, the clustering was almost perfect. This time, because the initialization was not good, we ended up with a clustering that is very far from the real distribution. So that's the reason why we use this parameter. We basically say it, run it twice, 3 times, 10 times, 20 times, and I want to keep the best model, because the result of k-means depends heavily on the actual initialization of the cluster centers. Which method is good for finding k-value for k-means algorithm? So as I was saying, so this is This is really dependent on the problem that is at hand. I mean, if you're, let's say I was giving an example, but let's say you want to see how similar the customers that you have are. And basically, in that case, you want to assign each customer to a salesperson. And you know that you have five salespeople. In that case, intuitively, you're going to use K as 5 so that you can assign a certain group of customers to a specific salesperson. And by doing this, basically, you're going to try to regroup all the customers that are similar to each other, and you're going to assign them to one salesperson. And then you're going to use, and then the other cluster, the other set of customers that are similar to each other are going to be assigned to another salesperson. So that's one aspect, basically. And that depends really on the problem. Another option is what we do is we try different values of K. And for each value of K, we're going to compute a cluster dissimilarity metric, basically. And we're going to see for each cluster how dissimilar are the observations within each cluster. And we're going to do that for different values of K, right? And then we're going to see at some point if, let's say, the optimal value is K star, if we have less, if we choose less clusters than the actual number, the real number, the dissimilarity might be high. And as we increase the number of clusters, technically we create less and more clusters, and that value can go down. But at some point, when we go from before the optimal number and after the optimal number, you're going to see a huge jump in the value of the sort of a kink. It's described that like in the value of the cluster dissimilarity, and you can use that as a reference, for example, to find the number of K values. Can you explain the parameter?
One more question, and then for anyone else who's in the program, you feel free to reach out or to post it on the R&D in the Slack group for everyone.
Yeah, you can reach out on the Slack. But so for the last question, can you explain the parameters of the function fit k-means? Yes. So basically, it takes here x is going to be the observations that we have. So the values that we generated here, we're going to pass them as arrays, as a matrix, basically. N clusters is the number of clusters, the value k that we predefine, right? Let's say we want k to be 5. This is the value that we're going to pass. Init is the type of initialization method. There are different initialization methods. In our case, I use random, and I said k-means as the default because it's the default being used by scikit, but you can play with this. So this is a type of initialization. And ninit is the number of times we want to initialize centers, and so the number of times we want to run the model.
Great. So let's maybe end it there. Sorry, Sarah. Please reach out to Mo on Slack, and let's thank Mo very much for that. It was fantastic. Really appreciate the time and effort you put into this workshop.
Thank you.
Merci, Mo.
Thank
Thanks,
you, Mo.
everyone.
Merci.